Hello, this is our final presentation for the fall of 2018 for CAE's senior project. We are doing the HoloLens with object detection and classification. This presentation is done by Timothy Jones, Brandon Nolan, and Ayana Tynes. First off, we would like to acknowledge three special people, one being Tom McCann, another being Stephen Briere. These are two guys who work at CAE, managers and principal engineer of software engineering. Lastly, but not least, we would like to acknowledge Professor Giovannetti. All right, in our presentation, we're going to be covering a couple of things. We're going to be once again recovering our background, moving towards our problem, covering the requirements once again, along with the design and the specifications of our final design. We're going to move on to the analysis of our final design, along with a quick overview of our project plan and how we have retargeted it for our current schedule. And then we're going to move on to our test plan. And finally, we're going to wrap it all up with our results and our future plans that could be for this project. A little bit back to background. CAE, founded in 1947, are specialists in training services for civil aviation, defense, security, and healthcare. And the device we were working with them was the Microsoft HoloLens. This is a device that cost a couple of $1,000s and is still currently in development, but it is responsible for providing holographic and virtual reality environment services for the user who wears the headset. And right now we are targeting the area of object detection and classification for this HoloLens headset. On to the problem. We still have the same problem. We wanted to develop a HoloLens application that will be able to interface between not only the HoloLens, but a server that operates or that is currently the host for our object detection software. Some of our requirements. Our requirements have changed a little bit per the request of CAE, but the user stories remain the same. Our snapshot is still a requirement, which would be from the HoloLens side, which would either have the user take a picture using the HoloLens and send it back to the server, or have the HoloLens itself choose an image from the library to send back to the server for detection. Another user story was the bounding box as well as label, which would have been returned upon the image being sent from the server back to the HoloLens. And some of our non-functional requirements included the implementation of a neural network in our object detection and classification, along with the server that was provided for on the desktop we were given to us by CAE, as well as an interfacing aspect, which was the interfacing between the HoloLens device and the desktop that contained the server running the object detection software. So a little bit more about our design specifications. At a really high level, you have simply the HoloLens and the server. Our server, we have a Aurora M5 Alienware desktop given to us by CAE, which has a dedicated graphics card, which is capable of having much higher processing power than any regular old laptop. And for the device, for the headset given, we have a Microsoft HoloLens device, which is capable of also rendering graphics in real time. On the lower level, we have the camera, the sensors, and the screen. These are aspects of the HoloLens device itself, responsible for taking the picture and actually doing many of the background aspects of this project, as well as on the server side we have Unity, which is a program responsible for developing apps and targeting them for the Microsoft HoloLens itself. Then on the last level, we have our object detection and classification, which is on our server side, which is the software we are developing, which is responsible for the actual detection of any objects in a given image.
For our project, the program primarily relies on object classification and detection. One of the main ideas behind object classification is the concept of machine learning. This is a series of algorithms that provides a program with a way of incorporating predictive methods during object detection. This algorithm is applied to a neural network, which is effectively a series of nodes that connects inputs to outputs that mimics the neural activity of the brain. For both our object detection and classification, we primarily rely on the program YOLO. As an example of how YOLO functions, an image is run through YOLO. Since YOLO is capable of processing more than one image simultaneously, it will put a bounding box around every object it detects in the image. It will then return the image to the user that has new bounding boxes applied. For our project, we incorporated a version of YOLO that is forked from a repository provided by Alexei AB. It requires an installation of Visual Studio's 2015, OpenCV, CUDA, and CUDNN. OpenCV is an open source computer vision and machine learning software library. CUDA is a parallel computing platform, and CUDNN utilizes CUDA in order to provide a library for deep neural networks. All of these are required to be installed in a specific order, with Visual Studios being installed last, or else it will provide hardware incompatibilities and other issues during compiling. The version of the YOLO that's provided comes with a series of pre-trained weights as well, although the training has to be done first in the code in order to actually have it function. We trained the system ourselves, and it took roughly 3 days of computing time in order to train the model to be at a place where it's able to fully detect objects. It came with roughly 36 objects that it was able of classifying, including cats, dogs, cars, motorcycles, bicycles, and people, as well as some other objects included. It's capable of providing close to a 99% accuracy on most of these objects. After our group was able to successfully compile the demo, we proceeded to move on to attempting to compile the simulator itself. For the simulator, we had 2 objects that we needed to put into the training model, which included the body of the simulator and the legs. Because we had so many less objects, our training time was roughly 2 hours compared to the 3 days that it took to train the model itself. In addition, we had a much smaller image library compared to YOLO's image library that it started with. YOLO's image library came with roughly 30,000 pictures, whereas our library came at about 30 images that we were able to utilize. And our image library primarily consisted of images of just the body, just the legs, or a collection of both the body and the legs. The expected results would have provided a bounding box around the full body of the simulator itself, as well as a bounding box around the legs underneath the simulator at the same time.
So now that we discussed our custom model, we want to talk a little bit about our features versus our user stories. This is a way for us to simply check to see whether or not our test plan lined up with the user story requirements that were given to us by CAE in the beginning of the semester. As you can see in the top, we have 2 of our test cases. One test case is to ensure object detection and classification run correctly on the desktop itself. This consisted of feeding the program an image or file path with the given image and analyzing the image given back to us by the program to see whether object detection was correct or not. And the second test consisted of us testing object detection and classification through the use of Microsoft HoloLens itself once we were able to port the object detection software YOLO onto the headset. Now the chart below these 2 test case items is our traceability matrix. This traceability matrix maps our corresponding user story requirements to our testing items. As you can see, most of the test requirements were met, including the server, the neural network, the ability to take a snapshot. However, the biggest thing that sticks out with our user requirements was our inability for us to actually load an image or take a snapshot to send to our desktop server. This comes into the aspect of the modular aspect of our user requirements, which required us to actually open an application on the HoloLens that would successfully open an image or take a snapshot on the HoloLens itself and send the image back to the server for object detection and classification to be run on the image.
After the results of our training, we were able to get the model to successfully identify when both the body and legs were present. However, they were never over the specific area where it was only the body and the legs. As you can see here on the image, the body itself is around this area here, and the legs are roughly in the same area, although not exactly on the same point. For what we wanted for the project, we needed the legs to be successfully in this area here, and the body to be roughly this area. We believe that part of the issue was due to the lack of images that we had during the training itself. With only 30 images, we didn't really have enough detection, we didn't have enough classification time spent. That's why our training time was so small compared to our training time for the demo itself. We had a lot more images to work on with that. In the future, if we wanted to increase the accuracy even more, we'd probably want to have more images of the large-scale picture of the body and the large-scale picture of the legs at different positions. So that way the YOLO detection is able to fully incorporate that.
To piggyback off of what Brandon just said, we want to ensure that we had the best model possible. And how do we know that we had the best model possible? Well, after training the limited amount of images that we had from CAE, we determined that after training so many times, after training for so many iterations, our model was the best it could possibly be. See, the training of any object detection or object classification library results on you running your training model through a certain number of iterations. These iterations can vary from 1 to 2 to 10 iterations, all the way up to thousands of iterations, up to maybe 50,000 iterations. And there comes a point in time to where you can analyze your data, you can analyze the amount of iterations you are performing on your training set, and you can see that your model is not getting any better no matter how many times you retry to train this model. And so that's what we did. We analyzed our data, and from there we concluded that our model had no more room to grow. There are even other variables at hand which can determine and factor in when you're looking at trying to improve your model, such as the learning rate. There's types of decay that happen. There are a number of filters you can apply to your neural network, and none of these values, no matter how much we change them, improve the model. So this is how we know we reached an apex in our training model, and it was time to take our results and try to get them onto the interfacing level. Now, after we have concluded that we have the best training model possible, it was on to HoloLens and its interfacing. Now, our first difficulty in actually interfacing with the HoloLens was determining whether or not the HoloLens could have a universal Windows application deployed onto it successfully. We first tried doing that with the HoloLens emulator, which was provided to us on the Microsoft website. The emulator does function exactly like the HoloLens itself, except it does not have the functionality of the camera since it's an emulator. And being that it did not have a camera, it did not do much good for us in the beginning stages of development. It's hard to open an app and test the camera if you can't access the camera. So the HoloLens emulator was an option that was tossed out, not quickly enough, but we learned along the lines that it wasn't going to be useful for us in the future. So, in moving forward with that, we were able to acquire HoloLens for development for the rest of the project. And of course, just a reminder, for this project, we were not using any cloud services. So basically, now we're trying to interface between the desktop we have and the HoloLens itself without the use of any online portals, basically directly interfacing between the desktop and itself. So we turned to a couple of different resources. The first resource we turned to was the Microsoft Mixed Reality Toolkit. This is probably the best toolkit, the best repository out there for developing HoloLens applications, period. There is an ongoing news thing where the HoloLens is still in current development, so there's not a lot of publication, there's not a lot of official articles out there on development of certain apps or certain things targeted for the HoloLens. So this repository from Microsoft was a great starting point for us to work on. It features many libraries and many pieces of C# code that can be used and integrated in a way to make the application customizable for the developer's needs. And so in the interfacing aspect of our project, we went for two methods. The first method was using a Unity project to develop a universal Windows application, and the second aspect was creating a C# project, which targeted a universal Windows application inside of a Visual Studio. The second option is Visual Studio solely versus the first option is basically solely operated on in Unity, and then after the project's developed in Unity, it is deployed through Visual Studio to the HoloLens. Now, we went with the first option, which was the Unity project, because we thought that it was easier to implement a scene and to work with the holographic environment in Unity. And these are results from here. So we found that image capturing, that is possible with pretty much any piece of code or any project you try to do. It's simple. It's as simple as calling the native camera app through the HoloLens or through a simple function call of the HoloLens camera API, which is a simple subroutine which just calls an application from another application. So image capturing wasn't our main problem with developing this HoloLens interface. The main problem we faced with the interfacing was the networking. If you don't have an ability to work with a cloud service or work with an online service to transmit and receive data, you're basically working directly with one host and another host. And there are solutions out there that people have stumbled upon and people have found that allow networking between the HoloLens and another device such as a desktop. However, these tools are not very accurate and are not very tailored for what our needs were. Sending a picture is very different than sending a message or sending bytes of data across a network. And so this was the main conundrum in our later development, getting the networking to actually function on our behalf. And so on the next slide, you're going to see a brief preview of what our HoloLens app could have looked like if we got the networking to operate correctly. So here I'm going to play you a quick video of what our demo looked like for a sample image on the HoloLens. As you can see here, we're just going to open the app. And when I click the app, you should see something similar to this if the networking's there. You should see the picture being sent and then this resulting picture being sent back to the HoloLens in an environment similar to this. And so looking ahead to the future, as we look back on this project, we saw that there were two main other solutions that could have been ventured upon. One of them was the Microsoft Azure Custom Vision API service. Now this is a cloud-based service, so it wasn't really useful for what we had our project tailored towards, which was something more offline, something more direct. But Microsoft's Azure Custom Vision service does a really great job at providing an interface that is friendly to the HoloLens. There is actually multiple Microsoft tutorials out there that allow the user to interact with pre-trained models and load them onto the HoloLens for the detection of their own choosing. The last option we could look at in the future was possibly the use of OneDrive to upload and download pictures from a remote server with YOLO Darknet. This would consist of creating an app on the HoloLens that accessed OneDrive, and when it uploaded a picture or it downloaded a picture, the server on the desktop could automatically run YOLO in the background and send the corresponding picture back up to OneDrive so you could open it up on the HoloLens. Thank you.